Alright, so here we go. Let's try this again. I'm futzing with some new software here, so you guys are going to have to kind of bear with me here. Alright, so this is problem 1 from the target check about conservation of energy with rotation. And so, let's see. So what we've got here is we've got this ramp. The problem tells us that it is, in fact, 4 meters long and inclined at 30 degrees. So the idea is our hoop is going to roll down from rest from the top down to the bottom. The fact that we are given information about the top and looking for information about the bottom is a strong indication that we probably want to use conservation of energy. And using conservation of energy requires us to know the height at a certain point. So let's call the bottom, we'll call this a height of 0. Use a little bit of SOHCAHTOA, and we can find that the height of the top is 2 meters. Okay. So, our general premise is going to be that total energy at the top is equal to the total energy at the bottom, right? Okay, so what types of energy do we have at the top? So at the top we've got gravitational potential energy, and that's got to equal, what types of energy do we have at the bottom? We actually have 2 types of energy at the bottom, right? We've got regular old kinetic energy because the hoop is moving. And then we've also got rotational kinetic energy at the bottom because the hoop is, in fact, rolling, right? Now, this is huge. Remember, you guys, that when you've got an object rolling, if the whole object is rolling, we can replace the combined kinetic energy and rotational kinetic energy with the following. It's 1 plus beta times the kinetic energy. All right, so then the question is, great, but what is beta? All right, well, remember, your beta is determined by the shape of your object. And for us, our shape is a hoop. All right, so if you look at the back of your equation sheet, there's that list of all the rotational inertias. And I, for a hoop, is mr squared. But notice there's no fraction in front of it. Usually the beta is the fraction in front. When there's no fraction in front, that's just 1, right? So that's what our beta is. So beta for a hoop is 1. Okay, so what that means for us then is this, oops, over here, this 1 plus beta becomes, whoa, stupid Microsoft. All right, so our 1 plus beta becomes 1 plus 1, which is 2 times our kinetic energy. And kinetic energy is just 1/2 mv squared. Notice 2 times a half is 1, so now I'm just looking at mv squared. All right. Then on the other side of the equation, we've got GPE, right? So GPE is mgh. So that's m times 9.8 times our height, which was 2 meters. So that's 19.6 m. Notice the m's cancel out. So take the square root of both sides, and the velocity turns out to be 4.43 meters per second. And that is question A. Okay, so let's see, what do we need here? I think that's all I need for this part of the problem. So I am going to clean up my board here. All right, and so we just decided that the velocity at the bottom was 4.43 meters a second. All right, now the rest of this is basically just using chapter 1 stuff with a little bit of jumper stuff. All right, so part B, my voice just did a weird thing there. Part B wants us to know what's the acceleration of the hoop. So let's think about the stuff we know. Well, the starting velocity of the hoop was 0. Final velocity at the bottom is this 4.43. We know that the hoop is going to roll through a displacement of 4 meters. So I think we can use this guy to find our acceleration, right? So plug in these numbers, do your algebra, your acceleration turns out to be 2.45 meters per second squared. All right. So then part C wants us to find the angular acceleration. So part C tells us the radius of the hoop is 0.35 meters, and it asks for the angular acceleration. So remember, anytime you know a linear or angular value and you're looking for the opposite counterpart, as long as you know your radius, you can use a jumper. Okay? Now remember, your jumpers are always linear equals angular times radius. All right? So for us, A, linear acceleration, equals alpha, angular acceleration, times radius. So some quick algebra tells us that alpha is A over R, which for us is 2.45 over 0.35. Notice this is meters per second squared. This is meters. The meters cancel out. Anytime you use a jumper, your angular quantity will have radians in it. Okay, and so when we solve this, you get 7 radians per second squared. Please remember, those jumper equations give you radians. Can't stress that enough. Okay, so that is C. D is very similar. D wants to know how many rotations it makes. So remember, how many rotations is equivalent to asking for the angle. Okay, so check it out though. We know our linear displacement and we know our radius. So I can once again use a jumper equation. Delta x is delta theta times r. That means delta theta is delta x over r. So for us, that's 4 meters divided by 0.35 meters. And it gives us 11.42. Again, I used a jumper, so this gives me radians. All right, so what I'm going to have to do now is I'm going to have to convert that to rotations. So I'm going to go times, let's see, there are 2 pi radians in 1 rotation. Now, please, please, please be careful. Anytime you divide by 2 pi, you got to put the 2 pi in parentheses on your calculator, okay? Otherwise, your calculator will divide by 2 and then multiply by pi because your calculator follows order of operations. All right, so if you figure this out, you get 1.82 rotations, and that is that. All right, so that is D. And then finally, E. We've already done the hard work for E. It says, how long does it take the hoop to roll down? I'm going to do E right here. Whoa. I'm going to do E right here. Check it out. I know VI, I know VF, I know delta X, I know A. So probably the easiest way to find the time is to use this guy. Solve for T. All right, let's see. VF is the 4.43. Our initial velocity was 0. Acceleration is 2.45 meters a second squared. Divide it out, and you get 1.81 seconds. All right, and that's it. All right.